Hi everyone, and welcome to the final lecture of this mini course in Einstein metrics. Please, Samsung, go ahead.
Yeah. Okay. Good morning or good evening, everyone. Let's as I said last time, the last lecture, we'll focus on the killer case, killer Einstein. Matrix. This is a so going back to our first lecture. So if you study Einstein metric in the most generality, it's not going to give much insight. There's not much structure, and it's very difficult. So then we have two special situations which are of interest. One is the case when dimension is 4, as I talked about in the last two lectures. And then there's also interaction with the special numbers, extra structures, special numbers, complex numbers, quaternions, and octonions. Those are discussed when we talk about the special holonomy. So now, particularly this scalar Einstein metric, this Einstein metrics, which are scalar, so it's you can say it's over compatible with the complex number system. So recall in our definition of a scalar metric, in terms of Riemannian metric, just if you have a Riemannian metric G, a Riemannian metric, and just say is scalar is scalar if let's say this in dimension m equals 2n, if the G scalar, if the holonomy group or restricted holonomy group, here I will consider the full holonomy group is contained in un. So before I put a 0 here, that means you consider loops which are contractible. But here we consider all loops. And what this means, this is a subgroup of SO2M. What this means is that there's a parallel compatible complex structure. J. So it is orthogonal with respect to G at every point. And of course, it's complex structure minus identity. And it's parallel with respect to the Levi-Civita connection and defined by G. And this condition is equivalent to saying, so when G and J are compatible, this induces a K2 form. So this parallel condition can be decoupled into two conditions. One is that J is integrable. So you can locally find the holomorphic coordinate and omega is closed. So this is a killer form. It means that locally. So now we will shift the viewpoint. So if you just consider Riemannian metric, and then you need this condition, which is just one condition. Now it decouples into two, and we can focus on first one. The first one just means it's integrable, so you have holomorphic coordinate, and then we study the meaning of the second condition. It's decoupled, right? So locally, It's a holomorphic coordinates. Z1 to Zn. So what it means is that you can find this complex coordinate. These are complex coordinates, and then the 1, 0 part, partial the alpha is square root alpha. So the 1, 0 tangent vectors are spanned by vectors of the form partial over partial z alpha. And then you can write down the omega. In terms of this, you can write omega. Omega is a real valued true form. So if you use this, and it's a type 1, because it is also compatible with G. So omega can be written as a square root 1 over 2 sum alpha beta G alpha beta bar d alpha wedge d beta bar. So this is a linear algebra. If you have over the standard complex vector space, if you have a true form which is of type 1 and it's real valued, then you can find you can write it in this complex basis of two forms, and then this G alpha beta bar is Hermitian, and because omega comes from the Riemann metric, this is actually positive definite. Excuse me, Hermitian matrix. And then, and of course, you have condition of d omega is 0. So if without that condition, you can always write the omega in this form, d omega 0. This is the condition. But then we can, as in Riemann and for Riemann matrix, so we can understand the curvature of the metric as the obstruction to make this G alpha beta bar standard through holomorphic coordinate change. So remember on Cn flat metric, standard flat metric, omega 0 is just some dz alpha by dz alpha bar. You can write as this as some alpha beta delta alpha beta dz alpha by dz beta bar. So we can locally choose coordinates, holomorphic coordinates, such that this G alpha beta bar at one point, this is standard, but then near one point. So it is standard at one point up to first order. So delta alpha beta, and then you have a second order, and then you can write the second order term. So the second order term would depend on alpha beta, but then you also expand, have two more indices. So 1/2 alpha beta, change to gamma delta R alpha beta bar gamma delta bar Z gamma Z delta bar plus third order. It's just that coordinate. And the reason you can make the first order, so this is second order, right? You can make the first order values because of the Kähler condition, closeness of omega. And then they can compute that. So we want to understand Einstein metric in this context, and then that involves Ricci curvature, and as I mentioned it in the first Ricci curvature, it comes from the expansion of the volume density. The volume density, is related determinant of G alpha beta bar. In the real coordinate, it's the square root of the determinant, but that matrix is exactly determinant of this complex matrix. And then this is a simple algebra beta. So just a contraction of this tensor, the beta bar. And this is the component. So this R of the alpha, beta bar, gamma, delta bar. These are components of the curvature tensor, and this is a component of the Ricci tensor. So remember, so we have a Ricci tensor of G. Right, this is a symmetric two tensor. And then it defines a Ricci form. It's like how you turn G to omega by compose with J. So this Ricci tensor you also compose with J. You get a form, two form, which are also denoted by Ricci. And this has a component. This can be written just like this. This is 1/2. Square root -1 sum alpha beta r alpha beta dz alpha wedge dz beta bar. Okay, so you just replace g alpha beta bar by this r alpha beta bar, which is the second order term in the Taylor expansion of the determinant. So then it's just from this it's not difficult to see that the Ricci form has the important fact that the Ricci form is closed. So d of Ricci equals 0. You can just do direct computation, or you just follow using the fact that you have this expansion. So that means so Ricci this is a real valued, R valued 1 form. So this means Ricci has a cohomology class, which is certainly a de Rham second cohomology class, but it's also a 1-1. So we just write H11 XR in terms of the Hodge decomposition. And this is exactly the same as the first Chen class of X is 2 pi, first Chen class of X. And if we consider as a cohomology class in H11 XR. This is also if you understand this computation is if you understand the definition of the first class, then it's essentially a follow from definition, because the first this determinant of its metric defines a Hermitian metric on the anti-canonical line bundle, and then normally if you have a Hermitian metric on a line bundle, the first class is defined. It can be computed using dd bar of log of that metric. You just compute dd bar log of this, and at this point you just get a Ricci form. And the first chain class of a manifold is the same as the first chain class of the anti-canonical line bundle. This is the same as pi first chain class of the kx inverse. Okay. So whenever you are given a Kähler metric, then the Ricci form is always closed, and it's in the fixed first class. It does not depend on which Kähler metric you choose. It's always in this class. And then naturally, if you do the Hodge theory, and you have a closed form, and you can ask this form to be co-closed, right? D star reach equals 0. What does this mean? This will be an equation, and by the Kähler identity, so D star is essentially the commutator of this left lambda operator and DC. But D of Ricci is 0, so it's just a D of it's the same as D of lambda Ricci, which is just the trace of Ricci curvature with the scalar curvature. Let's go back to see what do I use for scalar curvature? Do I use R or R? Yeah, not S. Okay, let's change it to R. And that's the same as saying R is constant. So this is a so-called a constant scalar curvature. It's just abbreviated as a C constant scalar curvature Kähler metric. Right. So a scalar Kähler metric has a constant scalar curvature if and only if its Ricci form is harmonic. Same as Ricci is harmonic with respect to the metric omega itself. A particular case, special case, is when the matrix Einstein, Kähler Einstein. Because Kähler Einstein just means it's a Kähler metric, which is Einstein. So it's here the Ricci form is a multiple of the Kähler form. This will imply scalar curvature is constant, and then the Ricci form is also harmonic. So this is the Kähler-Einstein equation. So in the Kähler case, Kähler metric to be Einstein, we need this equation. And immediately you see that if omega is Kähler-Einstein, there's a obstruction, there's a constraint on the manifold, because it will imply that the cohomology class of Ricci is lambda times the cohomology class of omega. But this is always 2 pi first chain class of X. Right, so having Kähler-Einstein will imply that the first chain class has to be proportional to the cohomology class of a Kähler form, and this is this only happens if what we call the first chain class is definite. Means it's either positive, 0, or negative. Positive means there is a cohomology class of Kähler form, such as lambda is positive, lambda equals 0, lambda is negative. So this is a numerical condition for the complex manifold. Right? So for example, when dimension of x equals 1 and that's why x is compact, then this first class the sign of lambda. First class is the same as the sign of the Euler characteristic. It's a positive for S2, 0 for high genus, so for torus, and negative for high genus surfaces. So there we also know in the first lecture, and any Riemann compact Riemann surface, it's a 19th century result. Every compact Riemann surface admits a Kähler Einstein metric. Kähler Einstein metric in that case. The two-dimensional metric is always Kähler. Mention this. If n equals 1 or m equals 2, the U1 is the same as SO2. So two-dimensional metric is always scalar. The complex structure J is given by the Hodge-Star operator. It is a J acting on one forms dual to vector field, given by the Hodge-Star operator on one forms. Right. So let's say the examples. This is a complex geometry. If you take a x inside, so these are examples of definite. First string has been definite. You take a x in CPN, which is cut by a generic homogeneous polynomial of degree d. So x is smooth, and then the first string class of x is positive if d is smaller than n plus 1, c1x equals 0 if d equals n plus 1, and c1x smaller than 0 if d is bigger than n plus 1. So you see that just look at this hyper surfaces. Sorry, it's a hyper surface. Cut out by a generic homogeneous polynomial of degree d, right? So most hypersurfaces will have C1 negative. Only for this finite many degrees you get a C1x positive. So C1x positive in algebra geometry normally it's called Fano manifold, and C1x equals 0. The Calabi-Yau, we will see in a minute why it's called Calabi-Yau, and C1x negative. It's kind of roughly speaking, it's called general type. It's a special case of general type manifold. So follow manifolds, they appear to be fewer than general type manifolds. So we already seen that if you have a Kähler manifold, let me say Kähler Einstein metric, then you have to have this topological obstruction, and then it was a conjecture, famous conjecture of Calabi, Calabi conjecture. 1954. That if X is compact, complex manifold. Okay, then this is also a sufficient condition. So X admits a Kähler Einstein metric if and only if the first class of X is definite. So this means the first class of X equals lambda omega for omega Kähler. Right? We already seen that this is necessary, and for the sufficiency, this is a conjecture, and that this will involve solving equations, solving the Einstein equation. Right? So if you just write down a random Kähler matrix, it's not going to satisfy an equation. This is what when we talk about holonomy. Right? So special holonomy, they are Kähler, they are Einstein, but there are two families. One is a generic holonomy, SOM, and the other one is this Kähler case, UN. They are not special holonomy. So why? Let's just then we go back to talk about explain the Kähler metric again, omega. So Kähler metric is a Riemannian metric, but if we shift we have already shifted viewpoints. When we talk about the Calabi conjecture, we are fixing the complex manifold, right? So when you remember the Kähler conjecture decouples once the complex purely depending on the complex structure. Just say that the manifold is complex, and then you have this extra closeness of omega. You know, this is we're now adopting that viewpoint. So we fix a complex structure. J and consider omega. So omega is closed two forms. So locally, it's always exact. It's a D of a one form, but there's a more importantly that's called the partial bar lemma. Something called DD bar lemma says that omega is not just a D of a one form. It's actually determined by a function. So locally, omega is given by square root partial bar of a function phi. Phi is a real valued function. Sometimes you also write omega equals DD bar, the DDC, or sometimes called DDC lemma. The relation is that so we know we can do operator D from one forms from P forms to P plus one, just exterior derivative. And because we have a complex structure, this DC is J composed with D, refers to D, and then you ichi omega P is decomposed into omega Q prime, right? It's holomorphic, anti-holomorphic part, and then J acts on each of them has is some power of square root minus one, and then you have DC. This is the point is that D and DC, they're both real operators. Real operator. They send real forms to real forms. real valued forms. And then you can write D equals a partial plus partial bar. So it's you project into the parts. So you are increasing the degree by 1, but then you are either increasing the holomorphic part or the anti-holomorphic part by 1. That's partial and the partial bar. And then DC will be square root of 1 partial bar minus partial. This is on functions. Omega 0. Right, so DDC lemma just means locally omega can be written as DDC of a function. And DDC, because just easily you can compute the DDC is twice square root of minus 1 of partial bar. Okay, so that's why when we write partial bar lemma, normally you have to put the root 1, otherwise the phi will not be real valued. Because when you conjugate the partial bar, it becomes partial bar partial, and then the anti-commute. And they put a square root of minus 1 here. That's conjugate. So this is a special property of complex geometry or several complex variables. You can always write this way. And then this phi, if you just write given a phi, you can do this. And this defines kilometric if and only for. I mean, you get a you will get a two form, and if we want it to correspond to metric, you need some positivity, and that's this phi is it's a partial. It's a complex Hessian alpha partial z beta bar. Second derivative with respect to z alpha z beta bar. This matrix has to be positive definite matrix, and if it's positive definite, then this is exactly up to constant multiple of the g alpha beta bar. So that's the matrix we get from the Kähler metric. Such a phi is called pluri subharmonic. So that's because in one dimension, if n equals 1, you are just considering such a thing. This is if I remember correctly, it's a fault. Something, some explicit 1/4. 1/4. The standard Laplacian, which is phi xx plus phi yy, right? And if this is a positive, it's called subharmonic function. And now this is a higher dimensional generalization. So pluri-subharmonic. This is the extremely important class of functions studied in several complex variables. Anyway, so this is locally omega is determined by a function. So that makes sense in Kähler geometry much simpler. In Riemannian geometry, when we talk about Riemannian matrix, you always have a big matrix to handle. Here, if you fix a complex structure, the Kähler matrix is just determined by a single function locally, right? This is first part is the local partial bar lemma. And local because we also have a global partial bar lemma means the following. So if we assume X is a complex, and omega is a Kähler form, and omega prime both Kähler metrics. And they are in the same cohomology class. Okay, this will imply that omega prime, they differ by a global function. dd bar of partial bar of a global function phi is So remember, so locally omega is part of power of 5, but if x is compact, so the point note 是它的globally omega cannot be of the form square root of part of power of 5. This is because otherwise the volume form is omega to the n over n factorial. This is the volume form of the metric G, and this has to be positive if you integrate over x. So, but if it's globally partial power of 5, then omega will be this will be exact. It will be 0. That would be possible. However, if you have two Kähler matrices in the same cohomology class, then they will differ by a function phi. Of course, if you're given omega, and then you can always add the square root of -1 partial about phi. If given omega, can add right this, and this is always well defined. But if you want it to be a Kähler metric, you need some positivity, which is not that this phi is pluralist harmonic, but locally, if you write the omega as square root of -1 of the divided per psi, you want per psi plus phi as some positivity. But if this phi is small, such as the derivative is also small comparing to omega, then you still get a Kähler form. So that means the space of all Kähler metrics in omega, this set is is an open set in the space of all functions. It's open, and of course we need to mod by R. So this phi is uniquely determined. So phi is unique, determined up to constant, always at the constant. So okay, so that's why we need to mod by constant. So this gives this explains why Kähler metric is not it does not satisfy equation. It's a it's basically open set in this infinite dimensional space, right? So from this we can just heuristically we can understand if X is compact, right? Then Kähler matrix compact manifold, not fixed in the compact. So Kähler matrix on X. So this is space of Kähler matrix on X, right? So that means it will involve a G and J and omega. But then you can somehow describe them in terms of in 3 steps. Okay. So first you have to prescribe complex structure J, and then you have to prescribe a Kähler class, which means is this omega is class cohomology class in H11XR. It's a class which can admit a Kähler metric. Some class may not admit any Kähler metric. For example, if you take a negative of this class, then there's no Kähler form. And then it's an extra function phi. So in either the local or global setting, this phi is called Kähler potential. It's a function, potential function that generates the metric. Okay, so in terms of complex geometry, the Kähler matrix on a compact manifold can be described in terms of the three data. So the first two, they are mainly complex geometry, or sometimes it's if you work with algebraic geometry, that's algebraic geometric. And the last piece of data is an infinite dimensional thing, right? And if you want the metric to be Kähler Einstein, you have to find some equation for this phi to be satisfied. And that's the next. So this Calabi conjecture is equivalent to solving a partial differential equation. So what's the equation, right? So suppose x omega is a compact Kähler manifold. So Ricci curvature omega may not be proportional to omega, right? But omega gives rise to a Hermitian metric. On kx inverse, because we assume 2 pi first chain class of x equals lambda omega. Okay. Assuming this. So that means lambda omega is in the first chain class of kx inverse. So it has to be a curvature of a Hermitian metric. Okay, with curvature. Minus lambda omega. Sorry, it's minus square root minus. You have to be careful. There's a coefficient anyway. So the first class is I over 2 pi times the curvature. Okay, so this is just view this first class as the first class of the anti-canonical line bundle. But then a metric on the anti-canonical line bundle gives a volume form. Omega. So why? So this is really a rather simple linear algebra. So you have at each point you have a complex line, right? You have a complex one-dimensional vector space, and you have a Hermitian metric on a complex vector one-dimensional vector space. That's just a element in the dual of this vector space. Tensor it's conjugate. So this is a section of the kx inverse dual, which is inverse dual, which the inverse is the same as dual. Tensor kx inverse dual. Because right, it's just a given norm, but this is the same as kx tensor kx bar, which is the space of this is just a bundle of top forms. That's and gives a because it's a positive. It's a Hermitian metric. It has a volume form. Okay, so one has to understand this first, and if you understand this, then the equation that the reach omega equals lambda omega can be interpreted as the fact that two volume forms are equal. One is omega, the other is little omega. Up to a constant. So I have to be careful. So the capital omega depends on little omega. Okay, so it's really both sides depends on omega. So this is um this is the equation. So if you're given just a little omega, it does not necessarily satisfy equation. Then what we do is yeah. So we want to change omega, right? In the same comolecule using this phi omega plus I dt bar of phi. This lambda of this will generate the so you're changing the curvature form by this, then the corresponding Hermitian metric. Let's maybe write down this. This is H. So the new H called H phi will be H times e to the negative phi. It's a formula for curvature. And then that's just by this not corresponds to omega phi is omega times e to the negative lambda phi. So that means the new for omega, we denote this by little omega phi. Okay, so Ricci of omega phi equals lambda omega phi. The same thing will be at omega phi to the nth power of, you don't need to divide it, have constant, c times omega phi, but which is the same as c capital omega, c e to the negative lambda phi capital omega. Or in other words, it's a capital omega plus partial bar phi to the nth power equals c e to the negative lambda phi omega. Okay, so this now looks more like a PDE. Capital omega, little omega is fixed, and we solving for phi, right? On the left-hand side, it involves partial bar phi, so it's a second derivative in phi, and it involves determinant. Okay? And on the right-hand side, there's no derivative on phi, but it's a very non-linear. It's a e to the negative lambda phi. Okay, so the Keeler-Einstein equation becomes this, and then the Calabi conjecture can be formulated more precisely. So X omega, you fix a compact Keeler manifold to start with, and then assume the omega, okay, and then the condition is that there exists phi such that this equation satisfied. For some constant C, so this is the existing part, and there's also a unique part. Is that there's a unique phi up to constant addition. Okay, it becomes the C equation. You can view this as kind of nonlinear Laplacian equation, like the general Einstein metric is also a nonlinear Laplacian equation for the remaining metric. Here, this is viewed as a nonlinear Laplacian equation for the function phi. Yes, if n equals 1, this is just a right, maybe just right. N equals 1. This is just the omega plus dd bar phi equals c e to negative lambda phi omega. But because n equals 1, just this is the same as taking the trace, so it's 1 plus Laplacian phi equals c e to negative lambda phi. And if you have a good memory of last lecture, this is the equation we wrote down for constant Gaussian curvature metric in terms of conformal change. Anyway, so now this is a Calabi conjecture. I think it's completely understood. So when the so literally it's not always true. It depends on this lambda. Lambda is the first chain class. So known. So lambda is negative. This is a result of O'Brien, Yao, 1970s, 77 or something. And lambda equals 0. It's Yao's solution to the Calabi conjecture. Normally, what people say. So this is the so-called Ricci. This is Ricci flat, the so-called Calabi-Yau metric. So, right, and later we'll talk about the lambda positive. The Calabi conjecture is not true on the nose. You have to modify it, and that's a much more reasonable result. But for these two cases, this the also the uniqueness also holds. Uniqueness also holds. Meaning that the solution is unique in these two cases, and that's not difficult. Uniqueness, and we can just prove it. So for example, let's consider the case lambda negative, omega plus square root of minus phi equals c e to negative lambda phi omega. Sorry, it's not omega and capital omega. But this is yeah, you have to be there's some function given, the known function. And when you take the trace of omega, little omega by capital omega by little omega. Anyway, the Gaussian curvature of the original metric. So let's go to this. So what we want to prove, this is unique. Suppose I have two solutions. So omega is itself a solution, and omega plus dd bar phi is also a solution, right? Let's see, omega. So by adjusting phi by a little constant, we may assume this c are the same. This c is the same as this c. Because lambda is non-zero, you adjust phi constant, you can always adjust this c upstairs. Assume these two c's are the same. And then this is essentially the same proof as in the one-dimensional case, it's the maximum principle. So let's consider at a point x, where phi x equals the maximum of phi. That's the minimum of phi. It's minimum of phi. then we know at the minimum the Hessian is non-negative. So that means square root partial bar phi is non-negative at x. So that means omega plus s. You think about this as matrix, it's bigger or equal than omega. But you can divide these two equations. You get omega plus dt bar phi to the n over omega to the n e to negative lambda phi. So at this point, this is bigger or equal than 1. So this means this is bigger or equal than 1. E to negative lambda phi of x bigger or equal than 1. So bigger or equal than 1. So that means negative lambda phi x bigger or equal than 0. Now negative lambda is positive. So that means phi x is non-negative. So that means phi x the minimum of phi, right? So the minimum of phi is non-negative. And similarly, maximum phi is non-positive. So that means phi is 0. Okay. Maximum phi is non-positive just by working at the maximum point. So you see that even for this uniqueness, it's very crucial. The sign of lambda is correct, right? If lambda is positive, then what you get it will be minimum phi is non-positive, and maximum phi is non-negative. That does not say much. So this proves the uniqueness when lambda is smaller than 0, and from here you already see the signs it matches. And when lambda equals 0, this will not work by maximum principle, but it's another. So that people say in PDE, and there are two techniques. One is the maximum principle, and the other one is integration by parts. So this here we have to do integration by parts. So when lambda equals 0 in the equation, there's no lambda. So basically, you just solve this equation, C omega and omega to the n is also C omega. They have the same volume. So again, the two C's are the same. So the basic just prescribing volume form. The two volume forms are the same. And then the technique is to, this is rather simple. You just consider this is difference is 0, and then you multiply by the function phi, and then you integrate. It's always 0, and then you integrate by parts. But before that, this you factorize it. You write as the difference, so a to the n minus b to the n. So it's a minus b, which is square root of minus d to the power 5, minus 1 d to the power 5, which, and then let's denote this by omega phi. So omega phi to the n minus 1 to n minus 1. This is 0. And then all these are closed forms. So you can do integration by parts. What you get is minus square root minus 1 partial phi, which partial bar phi, which this thing equals 0. And then you notice that each term is non-negative. Linear algebra, complex linear algebra. And it's 0 only if and only if every term this is partial phi, this one form is 0. Partial phi is constant. Okay, so this is the case when lambda equals 0, the uniqueness. And then see So the Calabi conjecture. So this is the Calabi conjecture for Killer Einstein actually mentioned that there's also a related Calabi conjecture, which is and Calabi conjecture 2. This is what's proved by Yao. It's basically the similar general case of the case when lambda equals 0. Is that if X is omega compact Kähler, then for you have a map from all the Kähler metric omega prime on X with omega prime in the same cohomology class, right? So this is a set, and you have a Ricci map, which is the first chain class of X. Just these are just the real valued, let's say more precisely, beta in omega 1 XR d beta equals 0. Just all representatives in this class. So the beta represent the 2 pi first chain class. Okay, so in other words, you can view it as a map from one cohomology class, which is the cohomology class of omega. So it's essentially omega plus partial power 5, and the other is the cohomology class of first chain class, is just Ricci omega plus partial power of some psi. Okay, so any phi you get a psi, and this map Ricci is bijective. So they have roughly similar size, right? Because each is just a open set in a space of functions. Actually, and the Calabi conjecture, another Calabi conjecture, this Ricci is a bijective map. So in particular, in the case when lambda equals 0, the Calabi conjecture, previous Calabi conjecture, is a special case when the first chain class is 0, because 0 is in the cohomology class 0, right? So you can choose a form where the Ricci form is 0. But more generally, it's prescribing the Ricci form of a Kähler metric. You can always uniquely prescribing the Ricci form of a Kähler metric in the Kähler class. So this is often very useful in complex geometry. Okay, so I think now maybe it's a good time to have a, let's say, 6 minutes. Continue. Okay, so I talk about the first 2 cases of the Calabi conjecture, and then the last case when lambda is positive, final case. So this is this on the one hand is more complicated, but more difficult. But it's on the other hand, it's actually more interesting. The point is that it's not true, not always true, that you can solve the equation. So when we even now even look at the equation, just the change in the sign, right? It's not a big deal, but from the viewpoint of a partial differential equation, that's really a big deal. So there are actually obstructions. There's further conditions on the complex manifold. That has to be satisfied. So the first one, I think it's Matsushima. I think it's 1950s, probably 1957. It says that if X is final, admits a Keller-Einstein metric, abbreviated as KE, then there's this automorphism group has to be reductive. So what does it mean? It really means that if you have a Keller-Einstein metric omega, then this automorphism group is the is a complexification of the automorphism group that preserve omega complexification. So what is the automorphism group? Right? This is just f from x to x. So diffeomorphism, preserve the complex structure of star j equals j. Holomorphic automorphism group, holomorphic transformations of x. And then this is a further, it's the isometry. If you f star j equals j and f star omega equals omega. So somehow in particular, so this is a compact group. This is compact. Okay. So means the automorphism group is a complexification of a compact group. So certainly there are many manifold where this is not true. For example, classic example, if you take a CP2, you blow up at 1 point or 2 points, then the automorphism group not reductive. You can compute it because automorphism group of CP2 is simple. It's just a PGL3C. It's a all 3 by 3 matrix. But if you blow up a point, it really does not depend on which point, but you can assume because by a automorphism group acting by automorphism of CP2, you can assume this point you blow up is, for example, it's 1 0 0. Blow up at 1 0 0. So anything, so then this will decrease the automorphism group because not every, so first every automorphism group of the blob has to be induced by automorphism of CP2. But in order for automorphism of CP2 to lift to automorphism of the blow-up, it has to fix the point of blow-up, right? So what is the automorphism? It's the action of what is the matrix that fixes 1 0 0? So it has to be something like this. This has to be 0. Right? So this is automorphism. This is not reductive. This is because so this is the reductive part is correspond to the first thing 0 0, and then this also has to be 0. Okay. This is because a compact. If you want, for example, if you want unitary matrix of this form, then if this is 0, then this also has to be 0. Or in other words, this part corresponds to translations, and that's not compact. That's not a can all come from complexification of a compact part. Okay, so it's not the same as the original group. So this is not reductive. Similarly, you can do for CP2 blob 2 points. So this is first obstruction, it's found by Matsushima, and then I think the second one is found by Otaki. Akito Futaki sensei. He's I think it's around 1980s. For what precise year? So what he introduced is it's called Futaki invariant. This has been very important in scalar geometry since then. So this is also concerning automorphism, but not this time, not on the group, but on the you just take its Lie algebra, okay, which is the same as the Lie algebra of holomorphic vector fields. So he defined a character or we call it FUT, is Lie algebra automorphism, homomorphism from this to C, where this is a trivial Lie algebra. Lie bracket is trivial. So if you have a vector holomorphic vector field V, then what you do is you choose a. So this is again X final, right? X final. And then choose omega in the first chain class of X. Because the first chain class is positive, choose a Kähler metric. And then this V will have a complex Hamiltonian HV. And then this Futaki invariant is defined as the integral of HV times reach omega minus omega wedge omega to the n minus 1. Okay, it's slightly complicated, but the point is that if you choose omega to be Kähler Einstein, then this has to be 0. But what Futaki shows is that this expression, this FUT, does not depend on the choice of omega. In other words, it's an invariant of the complex manifold. But at that time, it's just I mean, this is shown by taking derivatives. When you vary omega, you want to say it's invariant. But actually later, was found by Donaldson. There's actually a algebra geometric formula for the Futaki invariant. Do not need this integrals. Use the equivariant Riemann rock. Anyway, so but then and it's a Lie algebra homomorphism. So but the point is if X admit a Kähler Einstein metric, then this has to be identically 0 because you just choose omega to be Kähler Einstein. This part is 0. It's everything is 0. So you can also compute that for CP2 for previous examples, this not Futaki invariant do not vanish. So then, but both these two obstructions, Matsushima and Futaki obstructions, are related to holomorphic vector fields, automorphism group. But actually, there is a more conceptual reason why you shouldn't expect all final manifolds to admit K-line matrix. This has to do with the so-called jumping of complex structures. So this is the well-known fact that for final manifolds, some more general manifold, the space of a complex structures, moduli space of complex structures is not hostile. So you could have a family, right? You have a family, holomorphic family. So it's pi from x to delta. So each fiber is smooth in the funnel xt funnel manifold. But xt is isomorphic to xt prime when t is not equal to t prime is not 0. And xt is not isomorphic to x0. It is not 0. And so the complex structures they are isomorphic except the central fiber. Jumping up could this phenomenon can happen. So this implies that we consider J the we fix X as differentiable manifold, smooth manifold. We consider J to be or complex structure J on X such that the Xj is integrable and is a funnel. There's all the funnel complex structures on J, and K is all the Keller-Einstein matrix. That's J omega on X funnel, and furthermore, reach omega equals omega. Okay. So there is a natural map from K to J. Just sending J omega J. Just forget omega. But this infinite dimensional space will always modular equivalence, modular diffeomorphism group action. Okay. We consider two complex are the same if they differ by pullback by a diffeomorphism of X. Similarly for J omega. In any case, you get a natural map. For this map, let's call it phi. So phi is actually injective. This is this follows from the Bando-Mabuchi uniqueness. So we said that in the Calabi conjecture, lambda positive uniqueness is true, lambda 0 uniqueness is also true. Uniqueness of phi. And lambda positive uniqueness actually fails. Uniqueness of phi fails. But Bando-Mabuchi says that the following uniqueness is true. So if you have two Keller-Einstein matrix in 2 pi first chain class, then it's not true that omega phi differ by equal to omega as a Keller form, but omega prime differs by pullback by a holomorphic automorphism. Okay. So it's not unique as a tensor, so omega has a form, but it's unique geometrically because they differ by a holomorphic automorphism means that their geometry is still the same. For example, the curvature, right? There's the two metrics are isometric. And this implies phi is injective. It's basically just you fix complex structures, the omegas will differ by a diffeomorphism and preserve J. And we want to say that the phi is not surjective. But this is only a heuristic. Phi is not surjective. Okay, it's a heuristically. Why? Because otherwise, if you have a you have a this map is a kind of a continuous map, right? The left hand side is K is Hausdorff, and J is not Hausdorff. If phi is surjective, means bijective is continuous, and the Bandung-Mabuchi uniqueness, this is a heuristic part, right? So for each J, there's a unique one, and then you kind of expect if J varies continuously, then the corresponding omega also depends continuous on J. It implies that this is a heuristic part. Phi inverse is also continuous. So that means phi is a homeomorphism. But a Hausdorff space cannot be homeomorphic to a non-Hausdorff space. This is roughly speaking, the heuristically why we don't expect every Fano manifold to have a killer Einstein matrix, because then that will imply this complex structure moduli space will be canonically identified with the killer Einstein metric moduli space, but the complex moduli is not Hausdorff. The killer Einstein moduli space is Hausdorff. It's this moduli space of metrics. So this is heuristic, and this was the first known example where you don't have. This was I think the result of Tian in 1997. So this is the first result where this X and there exists X funnel where the automorphism group of X is trivial. So both the Fataki and the Matsushima obstruction do not obstruct, but X means no killer Einstein metric. And this X exactly has this jumping phenomenon. And then 10 introduced this called K stability. As a obstruction to this, and then this was later put in much more generally in algebraic geometric terms. It's the properties K stability by Tian Donaldson. This Donaldson uses equivariant Riemann rock to compute to give a definition of the K stability. Anyway, then so what's called Yao Tian Donaldson conjecture. That X admits a funnel, admits a KE metric if and only if X is K stable. So this is a subtle algebra geometric condition. I can explain a little bit heuristic. I mean, the precise definition is complicated, and more recently, it has been made much less geometrical by the algebra geometers. But we will explain a little bit more. But then the point is that this direction was the easier direction was known by Tian himself, and then Stopper, Berman. So a lot of generality. So this has a lot of this was already much older than 10 years ago, and this direction was proved by joint work with Chen and Donaldson. 2012. But then there were also many other approaches, new proofs of the theorem by many people. That's the interest data, Zakini and work with Chen and Wang using Ricci flow, and Berman, Song, Yangsen, Xi Li, and this is a more variational approach. So 20 more minutes, 5 minutes. Let's maybe explain a little bit more of this case stability. The picture is very geometrical. So let's explain this. So case stability. So the simple model is just a convex function. It's a strictly convex function on a real line. Okay. So for this. So if you have a convex function, when can it admit a critical point, right? So if you have a critical point, then it has to be a minimum point, right? And we show it in yellow. So if you have a critical point, then it must go like this. But it does not have to be the minimum point. It can go like this. The convex function itself can go like this. Then there's no minimum. There's no critical point. It's always monotone. But then here, and it goes to negative infinity. But it could also be having some kind of infimum at infinity, but never achieved, like this. Okay. So this are three cases, which is what we call this a stable case. It's an unstable case and semi-stable case. Stable case means you get a critical point. There's no critical point. Semi-stable means there's a critical point at infinity. Okay, so this is a condition of having. But how do you check if it has a critical point or not? Of course, if you know the whole picture, then of course you can see it. But there's a criterion just by looking at the behavior of this function at infinity, which is called slope at infinity. You can tell this because if it has a critical point, then the function has to grow in each direction. The function has to grow at infinity. The slope is always positive. But by this, I mean, for this, you have to go along in the direction where you go, and then the slope is positive. here, I mean, this slope is negative at infinity, but you have to go this direction. So the slope is actually positive. Here, in this picture, the slope is positive in this direction. It's growing, but this is negative. This is slope at infinity. It's negative in this direction, right? So this makes it unstable. So stable means slope in all directions at the slope at infinity is positive. Unstable means there is a direction where the slope at infinity is negative, and semi-stable means this is positive, but this at infinity is zero. And infinity is zero. So it's kind of a borderline case. Zero. So the notion of K-stability for final manifold was introduced exactly can understand exactly in terms of this, but now one has to understand what is the space and what is the function and what is the slope. If you understand all this, then you can formulate it. But the situation is much more complex already. If it's not in R, if it's in R2, the statement that a convex function has a critical point if and only if the slope along each direction is positive or non-negative. This is already not easy to see, or may not be clear. It's actually true. You can just look by looking at the directions along straight lines. Right. So what is space? The space is called the space of Kähler matrix. It's exactly the space of all Kähler forms in the same cohomology class. Fix x omega, the funnel, and the space we consider is space of Kähler potentials. H, which is space of all smooth functions of x such that omega phi equals omega plus this is positive. So it's probably also, I mean, it's natural that because of Einstein equation is a variational problem. It's the Euler-Lagrange equation of the Einstein-Hilbert functional. But now if we restrict to the space of Kähler potentials, then the Einstein-Hilbert function will not be good because that's a constant here. But there's another another function. But before the seeking the function, one understand the structure. And this is very interesting. So this space is a subspace of the space of all functions, the open set. And it has got a natural metric, Riemannian metric, infinite dimensional. It was introduced by Mapuche, Simmons, and Donaldson independently, but at different times. So it's natural. So if you take a phi in H, the tangent space of phi is identified with smooth functions because this open set. If you take 2 points, phi 1, phi 2, in this, then I define phi 1, phi 2, the Riemannian matrix pairing at the point of phi to be the natural L2 inner product omega phi with respect to omega phi. So this is it's a metric, and one can actually compute the geometry of this metric. For example, the curvature, and one find out that this is formally a locally symmetric space. It's a symmetric space. The covariant derivative of the curvature tensor is 0, and the sectional curvature is non-positive. So it should resemble the space GLN C modulo UN. It's like a symmetric space, non-compact symmetric space of type the GC mod G, KC mod K. Compact group complexification modulo K. Anyway, so it's a non-positive curve, and then one expects that this is every 2 points can be connected by a unique geodesic exponential map and stuff. It's that all formal, but mathematically there has been a lot of work in this direction, and a lot has been made rigorous. We will not delve into that. But then the point is that this is a space. It's not like Rn, but it still has a lot of directions going to infinity, and that is good if we want to detect the convex function. But what is a convex function? The function is called the Mabuchi functional. Introduced by Mabuchi. And this function was introduced as a primitive of one form. So you define a one form on H. And it's a very formal, but you can all make you can make precise, but just for computation. So what is the form? Let's say alpha. So at phi in H, you take a psi in the tangent space, which is C infinity functions. The alpha at phi, so it's the x on a tangent vector. It should give you a number, and the number is given by, again, in L2 inner product. But you are pairing psi with something else. What is the other function? The other function is has to do with phi, and for phi, the natural function comes from the geometry of the metric. It's a scalar curvature. But you can also write it in this way as Ricci curvature of omega phi minus omega phi, which omega phi to the n minus 1. But this is actually the same as a scalar curvature of omega phi minus n omega phi to the n, something like this. So this is a one form, and this one form has a property that it is closed, d alpha equals 0. And this is what has to be computed. And because it's closed and this space is contractible, okay? Any potential, you can just linearly interpolate them. This is contractible. H is contractible. Contractible. So this implies that alpha is d of a function, and this function is a Mabuchi functional. So E is a Mabuchi function. But this E is not actually a well-defined functional on the nose. It up to a constant. That the constant does not change the waveform. It has two properties. First is obvious that critical point of E. They are exactly killer Einstein metrics. That's if this is 0 for all psi, then this has to be 0. And second is that E is convex on H along geodesics. Right. So this involves computation. This not magic. Okay, it comes there are some interpretation, but that's more complicated, and we will not talk about that. Okay, so now we also got the function. We are this exactly becomes the problem of finding the critical point of a convex function on space, and then by the heuristic, as a one-dimensional model, this thing has a critical point. The existence of Kähler-Einstein should be detected by whether the slope at infinity along the geodesic along a direction is always positive, and that is K-stability. K-stability, roughly speaking. Slope at infinity of this function E along here along direction along a geodesic ray and positive. But this sounds rather formal and infinite dimensional transcendental. There's no algebraic geometry. And then to the actual algebraic geometry is actually to approximate this using algebraic geometry. And it is amazing that this approximation actually works. How do we approximate this? So this is your space H, and you are going to infinity along a ray. So that means you have a family of omega phi t, right? This metric has going to infinity means it has to degenerate. And algebraic approximation of this is called test configuration. It's terminology. But it just means that you embed X into some CPN, okay, embed. You first embed, and then you take a one parameter subgroup, the one parameter subgroup of PGLM plus one, the automorphism of CPN, and then you degenerate this variety X along this direction, lambda T, and when T go to 0, you may get something else, X0. And then point is here, X0 could be singular. But X0 is fixed by lambda T. The C star action. Okay. You have X, you have something and you push it using this one primary subgroup. You will get something in the limit. The limit could be singular, but the limit will not be pushed further. You will be preserved by this action. And this is approximation of this geodesic ray going to infinity. And then you can for this, then you for Taki invariant can be defined on X0. Okay, so this means it is a slope at infinity. So Y is a Fataki invariant, right? We know that Fataki invariant is something we define, and it involves go back to Fataki invariant. It involves holomorphic vector field. And suppose X0 is smooth, then the holomorphic is just the vector field that generates a sister action. So you have Fataki invariant, that's fine. But why this has to do with Mabuchi, Fataki and Mabuchi, how they're related? This is again, you can, if you look at the formula, they're closely related because the Mabuchi functional is derivative is like this. Okay, and the Fataki invariant is just the same formula, except this function is the Hamiltonian function for the vector field. So, but actually, so this last bit is that the Fataki invariant is the derivative. Fataki invariant is the derivative of Mabuchi functional along holomorphic vector. Mabuchi functional along the direction, the action of automorphism X. Okay, so that explains that this Fataki invariant can be viewed as a slope at infinity of this function. So well, maybe I should explain this. The sentence it just means the automorphism of X on H omega to F star omega plus bar 5 to F star omega plus d bar 5. So there's a problem with the constant translation by a constant, but let's forget about that. And then the point is that so you have infinite dimensional space. You have this group acting on H, and this action, so it generates. So for any V in the Lie algebra of automorphism X, you get a vector field. Let's call it little v on H. And this just from this property, this is a canonical action. This little v preserves the one form alpha. And by Cartan formula, d of little v contract alpha plus little v contract d alpha equals 0. Alpha is closed. That means this is constant. This constant in H means it's something independent of the metric. And this is exactly the Fataki invariant of V up to constant. It's constant on H. Means it's independent of the choice of omega. Okay, so this briefly explains the picture why the expect such a thing. But of course, the actual proof of any of this will involve a lot of work. Okay, so I have 5 minutes left. So maybe I've prepared other things, but we don't have time. But I just want to say that for Kähler-Einstein matrix, the existence problem is solved, and then there are still other interesting things about this. One is about the moduli space and the singularity formation. So one type of singularity is a conical singularity. So it modeled on a cone. Okay, if you want a cone to be Kähler, this has to be Ricci flat Kähler cone. So this the link, the cross section y that correspond to the cone over y, and this corresponds to this y Sasaki Einstein. And so it's a singularity model for this matrix, and this is very important. And it has an interesting thing in physics. It appears in ADS-CFT. But it's there are some relation with using this, and in particular in there's Martelli Sparks, Yao Sparks, and other people. So this Sasaki Einstein matrix has a Sasaki Einstein has a volume minimization property. Is what I read is a dual to some A maximization in some field theory. But mathematically, this has a consequence that this has a volume of Sasaki Einstein metric. It's normalized. So Ricci G is G. Is an algebraic number. Okay. In Q bar. Okay. So it's known that the volume is not always a rational number, but it's always an algebraic number. This is it's a very interesting, and it also has a lot of applications in study of the singularities. It's important applications. And another thing is for especially for Calabi-Yau matrix. What is another kind of is collapsing to lower dimensions. Interesting things. One is this SYZ or conservative Schwaberman conjecture. For large complex limit or for general complex limit, it has to collapse along some nice directions, and the limit should be described in terms of the degeneration. But also it also in algebra geometry, there's a so-called abundance conjecture. For in the Calabi-Yau case, it just corresponds to that if you have some class which is on the boundary of the killer cone, does not consider contain killer metric, but it's not negative somehow. Then you expect this as the killer class move to this point, the Calabi-Yau metric should collapse along some holomorphic fibrations. There are many questions. Yeah, I think if you are interested, you can look up references. It's a lot of active directions. Yeah, thank you for coming for lectures.